Thanks for having us come and talk a little bit about our project that we did. As you can see, we worked on the distillation control project. What our objective was to analyze three different techniques of control and how they did compared to one another. We did non-interacting PID control, interacting, and then also the non-linear. And we analyzed each of them and found which one was the best. First of all, what we had to do was get a model. So we derived this single trait model for the distillation column, and with that we were able to find out how the model reacted to different manipulated variables. The two manipulated variables we have is the reflux ratio and FBOT, which is the fraction of the feed exiting the bottoms, and then we analyzed how those affected each of the compositions coming out of the top of the distillate and coming out of the bottoms as well. And what we had to do is extract data from MATLAB as to that described that model. We took a long time to do that, but we finally were able to. Jonathan was actually able to find a way to get that data out, and so then we could put it into Loop Pro software and fit it to a first order plus dead time model. And these are the transfer functions that you see here that describe each of those manipulated variables affecting the controlled variables. And then once we had these transfer functions, we could run a relative gain array analysis. This is the matrix that it generated. As you can see, the reflux ratio will be paired with the top composition, and the FBOT will be paired with the bottom composition. And that's what we were able to do. And then after we had these, we were able to run the different controllers in Simulink, and Jonathan's going to talk a little bit about that.
So in Simulink, this is the model for interacting controller, but the non-interacting controller just has all of these feed-forward controllers taken off. So let me kind of point and show you what's going on here. So the top part of this is for the control for the composition in the top, and then the bottom is for the bottom. The models are here and here. Where is it? Here.
Yeah.
And then we've added some feed disturbance as well as disturbance due to the top acting on the bottom and the bottom acting on the top. And so we've tested and found what those disturbances are, and they're labeled here in gold. And then we have feed forward control that drives the process to the set point. And then there are set point changes here and here. And so when we test all of that together, we can prove that the interacting control is working or see if it's not. Are there any questions about this? Does that make sense?
Yeah, it makes sense.
Okay.
So next we've got our results, and the graphs on the left-hand side are for the fraction in the distillate composition, and then the ones on the right are for the bottoms. And I want to point out first that you can see how our interacting control isn't graphed with the non-interacting and non-linear, because we had some issues with getting the data from Simulink to be on the same time scale. We were working with that, but it would give us more data points because the PID controller we ran just in MATLAB and got it from APMonitor. But we tried to make the scales as close as we could to look and compare. So first I want to highlight the green lines on each of the top are our non-interacting PID controller response. And in the tops, it was pretty good at rejecting disturbances here and for tracking the set point, even though there was a little bit of a lag. In the bottom, it wasn't quite as good since it spiked up pretty high. And so we can see on the same graph, the nonlinear control response was much better in the bottoms than the PID controller. Did a great job at rejecting the disturbances. We weren't sure in the tops exactly why it dipped down so low from the feed disturbances that occurred. But since we didn't look much into the equations, we don't understand completely why that happened. But then for our interacting control, looking at the top composition with the set point changes, it did a great job of of tracking the first set point change, and you can see a couple of spikes up and down. We're not sure if that's a bug in the code or exactly what that is, because those don't correspond with specific feed disturbance changes. But for the general trend of tracking the set point, it did a good job. However, in the bottoms, we somehow managed to defy the laws of physics by having a negative mole fraction of cyclohexane in the bottom. So we acknowledge that we have an issue with our Simulink model right now. We were working on it last night and trying to figure out why it was giving such big changes all the way up to 0.35 when the other controllers didn't even reach 0.07 mole fraction. So that's an issue that we could still work out. But in conclusion, we believe that from these three controllers that the nonlinear control performed the best, especially in the bottoms. But since we have that bug in our Simulink model, and since we weren't able to exactly line them up and compare the three on the exact same time scale, we believe that the interacting controller could perform as well as the nonlinear controller if we were able to optimize the model. But we're grateful for this opportunity that we've had to work on this and learned a lot. So, are there any questions?